I'm currently a postdoc of Professor Imran at PhD at CI. I will be associate professor in 2023. So I'm going to talk about some one correction about inflationary power spectrum. The contents is I heard that this is a summer school for students. So I try to find, I try to include some very basic theory. So this is about standard primary gravitation. Opinion. Then I'm going to review some conduit correction. For primary gravitation waves. And then I want to focus on the relationship primary black hole formation and primary gravitational. And finally, I will go into the main topic, which is about the one-loop effect. Or this stuff. This is my plan of this talk, and let's start with the first one. Sure. I wasn't here for the morning, so probably Professor Wang is already told.
We talk about scatter perturbation, but not gravitational wave.
Okay. So we start from metric of the state of the quantum unit. A square and square. Alright, so this is the line elements of what we have. Something different from the scalar case that we have H yet. So this is the perturbation of the space component, and we normally impose the traceless transfer with H. The traceless condition means that this Hij does not change the volume. The volume factor is unchanged, and the derivative of Hij is zero, which means the gravitational waves are cancelled. So this is the setup, and our action for question. We have the total action is. So this is the volume element, and we have something related, something for inflation, whatever it is, scalar field models, which drives the inflation. Then we have the Einstein field of action. So this is the 4D curvature, and which is composed of the derivative of this metric. And actually, this curvature is written by the square of the derivative of the concept of. So this part is, by solving the background equation of motion, we can find some inflation. On top of this inflation impact, we consider the part of it, the tensor part of it, which is the gravity. So if you expand this part up to second order, we have the second order, which is hi dot h. So this is nothing, but this is very quite similar form that is. So this is very similar to the action for the scalar. We have the derivative, the square of the velocity and the square of the gradient. So this is like a harmonic oscillator, like scalar. So we can quantize Hij by imposing canonical quantization condition for Hij and its conjugate mode. So if you do canonical quantization, you will find an operator Hij. Then you get correlation function of Hij. At some time out and in Fourier space at some Fourier number Q. This is usually characterized. So this is the power spectrum which we also saw in scalar objects. But now we are interested in spectrum. And in this case, this pH is 4 times H input divided by n prime squared. So in contrast to the scalar fluctuations, we do not have epsilon. So this thing is directly related to energy scale of inflation, which is the square of Hubble range. So finding a gravitational wave path spectrum in the present universe is very important, because if you find it, we will know what's the energy scale of the whole inflation. So actually, we usually consider the polarization of the CMB sky, and that is the signature of gravitational wave. So so far I'm doing pre-theory. So I would say this is pre-level aspect. Today's talk is about one loop effect. What is the one loop effect? Final gravitational waves. So what does this one loop mean? So the thing is, gravity is something. So the nonlinear interactions are inevitable if you think of gravity. For example, let's consider a scalar. Sigma on top of the inflationary background, which we consider previously. Pre-scalarity, the action is so now we have the kinetic one, and as we saw, Aj is inside the reality. So this is a way this type of coupling between the scalar field and U is called minimal couple, which means this sigma field is gravity like us, as usual. So this defines how sigma moves in expanding. So the thing is, G nu with lower index has HIJ, at the linear. So if you derive the inverse of G nu, HIJ appears as normal. And it will not never stop to any point in terms of H. So the nonlinear coupling between HIJ and some field is inevitable and is very unique. So the question is, if you have coupling like this, what is the effect on HIJ? And then this is the nonlinear coupling, so we are thinking. This is actually what we usually do in the textbook of quantum field theory. And the thing is, we cannot solve the interacting system, which means we cannot find, there is no Green's function for a general nonlinear equation, differential equation. So we have to do this alternatively, which means we first solve the equation motion for linear order, and then expanding the solution by using this field. So in quantum field theory textbook, we are interested in the cross-section of this some scattering process. But in cosmology, we are interested in correlation function in the sky. So we are more interested in informers rather than in outformers. So in informerism, we are interested in the evolution of the HIJ. So this is productively expand, and there is a formula which formula. So this HIJ bar means the free, and the free field is expanded by time integral of the interaction Hamiltonian and commutator with HIJ. So this is the leading order effect, which is the Born approximation for the mean field appears in here. And this expansion is always, we have a higher order. So this expansion expands to English. So now in the previous board, we computed HIJ and just computed the prospect. But now we include this higher effect, and we are going to study the whole prospect. So the rest of the part is very complicated numerical and algebraic calculation. So I want to show you more in more easy way to understand the result by using a Feynman. So what kind of terms are here? So we can imagine HIJ is here. So the I sigma over sigma. So we have this kind of and also we have some coefficient and H the second order reference. We don't know what. We have some. So this is the 3-point interaction between HIJ and some scalar field. And this is 4-point interaction. So we have this kind of interactions and all higher order. But at least up to 100 order, these two interaction is, more complicated diagrams are always higher orders. So we can function. Now, okay, let's write one loop diagram. So what kind of combination is possible? The first, probably, can use this one, this 4-point integral. So let's take one. Can contract these two scalars and Green's without Green's function graph. This kind of structure. And also, we have this kind of which comes from two old correlation of 3.1, which means once we scatter here, and again we scatter. So this is the second order step. Okay. So this is the standard way to write down possible diagrams in QFT. But as I said, we are doing in format, which is a bit different from the standard in-out formalism. The propagators appears in the in format are a little bit different. In in-out formalism, we only have the propagator. But for the in-out formalism, we only have the propagator once you fix the B. But for the in formalism, the way of the contraction is big. And then we have we not only the retarded Green's function, but also we have the so-called statistical property, which is like aspect of the linear. Or we can say Taylor's Green's function, whatever. There are some. So I use this symbol. Just line corresponds to the retarded Green's function, which the propagation of this thing. And another is with this circle and the cross, which is the statistical property of Taylor's Green's function, which is the generation of the speed from. So this is like something like source, and this is something like is it like yes. And actually, when you write this kind of structure, this circle is the source Taylor's Green's function, because you contract this, you have the bus. And also, the one of the external line has Taylor's Green's. So this means that the gravitational wave produced here, and to the right, this propagates back. And to the left, this interact with galaxies and propagate along the direction. And for this diagram, actually there are two possibilities. First one is we have the Taylor's Green's function inside. So which means we have the source here. So this is so-called induced gravitation. From nothing, gravitational waves, scalar fields are generated and it interacts and propagates. But another possible diagram is something like this. So we have one source, but we have a propagation of the scalar. Okay. And then here is the source of the gravitation. So these three diagrams are actually appearing in the one loop calculation for the primary gravitation. Questions so far?
the GK on the starting line is the same or different from the GK on orbital?
The GK for graviton is h squared divided by n times. And GK for scalar field is also the same. But GK for curvature particle is divided by it.
The first scalar doesn't divide and blank, just the x squared over pi is like.
Yeah, for Planck dimension. Okay, so far I was talking about thermal gravitational waves.
You mentioned there are curvature perturbation, scalar perturbation, or scalar curvature is the same.
Now I just have inflationary background and if it has scalar field, some scalar field. It could be inflaton propagation or any other spectrum. I don't specify. There are some scalar field. And then what's the effect of this on x?
Yeah, basically
Yes.
one.
So the standard result, which means if you just think of this sigma field is like a vacuum fluctuation during inflation, then this one loop result is very well known. This is just the so one loop fraction divided by the p level is 1 plus and normalization sketch. So this is the very well known. What is important? Because now we have some loops. And if you have loops, we can have UV divergence or some divergence. So we have to regularize the integral and remove the divergence. So we have some okay. So this is whatever the number is. This is set 1 n. So the thing is, here is a very small factor, h inflation squared divided. So this is, the same size as field. So if you go to the higher order, we have more h squared over square. So normally, the one fraction for the standard normal vacuum scalar is quite small.
The numerator naturally the full contribution goes to the one. Otherwise, you don't have much one factor.
My point is this. So we can rely on the first order linear calibration theory for this to discuss the Feynman calibration.
Become fluid. Fluid.
Okay, so far so good. This is the standard case. And let's just, how many minutes do you have?
It's okay.
It's okay. Okay.
It's the next time.
Okay, so now let's go a bit different direction. Feynman black holes. Feynman black holes. I think Feynman black holes have been okay. There is. So probably you can be ready. And why this is so interesting? This is very creative scenario. Gravitational, black holes are formed from the collapse of all horizons at some moment. It's very crazy. But we have this event, W1.5.1.4. So this event detects 30 solar mass black holes. So for the black holes from supernova explosion, this is probably a few solar masses. So this is much bigger than the standard the naive black hole which we expect from a solar scenario. Also, we know that, almost know that, there is a supermassive in pores of galaxies. So this, I don't know the number, how supermassive, but the thing is, there is a huge black holes, and those black holes could be also there in the very early time. And we don't know how those black holes are formed. So one possible explanation to those, the formation of those black holes are primordial black holes. So what is the primordial black holes? So I don't think I have to do this, but so if you think of this. We have the curvature fluctuation that could be very huge at some point. So what happens? This is the Friedman FLRW metric, and the Friedman equation for this system is usually we consider radiation domain.
Sorry, I'm in the platform.
Usually we think the universe is dominated by radiation during the early universe. This is proportional to beta minus 2. And if you have curvature fluctuation, we have the back reaction background. And the energy contribution of this curvature fluctuation. This is the energy density of Hubble. This is 4. And this is beta minus 2. So, as far as beta is small, this is subdominant. Always, the background radiation is important. But if curvature is not so small, like it's 5, if it's like 0.0, 0.1 or something like that, at some point, this 8 to the minus 4 decay, always this is faster than the decay of minus 2. And at some point, this energy get bigger, and the universe is dominated by curvature. And if the universe is dominated by curvature energy density, this universe is spatially coupled. And the fate of the spatially coupled universe is the big quench, which means the Friedman universe up to I think is pointing. So this is the formation of black holes, and this can happen in the very early universe. So we call this. So now the thing is, this curvature fluctuation, if this is huge, primordial black holes can happen. Large curvature fluctuation can be sourced by large interactions, as she said in previous talk. But perhaps maybe we can have some other fields like sigma, whatever it is, and then sigma can produce large curvature fluctuation.
Does the sign and the
Yes, sign and also curvature. I mean,
Yeah,
the second derivative.
plus the sign. And the spherical geometry.
Yeah.
That's good.
I think it depends on the shape. I mean, actual form. I can't remember.
So, for example, Z is symmetric. Z.
Second, sorry.
And so you consider a transformation that takes zeta to minus c, then the rho zeta will not be very much.
Yeah, I think the final conclusion is invariant. Critical sign. Yeah, you have to be complete. Anyway, so large curvature might come from large scale propagation during the inquiry. So what happens if you have large scale propagation? That affects the loop correction for the gravitational wave. So this is the idea of bubble. So now I explain the motivation to think of excited scalar. If you have some such a scalar field, we might have a large character, which can't explain from. So I don't care what's the actual model is. Let's say there is a additional scalar field, which is enhanced, excited at some point. So as usual, the scalar field is bounded. It's really so in our case, we have a formula. Let's consider this mode function. At some point, B is B star. Is multiplied by a beta. This factor in our model is equal to exponential. Some time constant. So this is the physical time, the initial time of amplification, and time with. In conformal time, this is the power. So we take this mode. So at some point, at some therapy star, we have some spike like excitation for this scalar field, and the amplification factor is some point. So typically, if you think of the parametric resonance, we can have some.
So P is similar to P.
P is the rhythm, and here is the model function.
already
Yeah, so
in a non-trivial state.
yes. So we have the equation of motion for scalar field, and this UK is the solution to it.
Usually, in a trivial state, the canonical commutation related to fix this, but not in a trivial state.
Right.
Oh, sorry, I'm lost. That's the K is the co-moving wave number, but the P is the
The same, sorry.
the same.
So I didn't.
Oh.
Those. So the point is, I'm not going to the detail. The point is, we assume that there is a excited point, and which is that. But this time dependence doesn't matter. So the thing is, at some point, at some scale, we excitation. So what happened? Now, if you multiply the mode functions by some amount, then naively speaking, this Green's function, here is Green's function. Also, in this case, this amplification implies that the equation of motion itself is changed, and which and then this for this equation of motion, Green's function is constructed from two compressed conjugator, and that was so. As a result, this Green's function has also by square. So maybe speaking, the building blocks of this one equation is much derived by a big factor, which so sometimes depending on how you amplify, and if you mix U, E, and star to amplify and to like we will transmit this really fast depending on combination. But if you just multiply by the both the derivatives and the Green's functions are multiplied. So all we have to do is to just combine this and integrate like here for example. So apparently, this is the this we only have one scalar propagator. So this is not right. And this has two scalar propagators. 4. And this has one scalar propagator. It's statistical propagator. And Green's function. And 2. So these two terms are more amplified. You have some Gauss excitation for scalar. What's the result? Yeah, I thought under divided by 3. The first, let's see this part. This part is we already know very. People already know very. This is the induced gravitation. So the scalar field has intensity fluctuation, and this has velocity and something like this, and it really produces the gravitational wave. It emits gravity.
Excuse me, I think some point, what bring this amplification factor? What the physics bring the amplification factor?
This is a model. We just assume.
Okay.
Yes, but many people consider many primary black hole models. So there are some. Okay, so this is the induced gravitational waves, and we consider excitation for P for this Z and P for P star. Typically, we have a scale. So this is the scale of the fluctuation, excited fluctuation. So this induced gravitational wave section. So this is P star, and above P star we don't have anything. So this is because from this process there is a conservation for the momentum between the four. And the thing is, here is a peak around this star. So the gravitational waves emitted from some structure, the size of this gravitational wave is equal to this scale. So we have this peak. And here is the Q count. So this means that even if you have a catastrophic scalar fluctuation at some very short scale, we will not see this effect in the CME scale, for example. Because this is causally disconnected. On the other hand, this type of diagram, this type of diagram, this is not an induced gravitation. This is so this is the correlation function between linear tensor mode and nonlinear tensor. And this is the, I would say, some modification on top of the already existing gravitational wave. So, and then this type of okay. The point is that the correction from this type of frequency. Okay. So I said this CMB scale is very short and large scale, which is causally disconnected from this short scale. But this gravitational waves are already there from the correction. And on top of that, we have some nonlinear effects. And so simultaneously, gravitational waves are reduced or down, or amplified by IR region. So it does not violate causality because it was originally given. But the thing is, initial gravitational wave can be multiplied. This is greater. So the thing is, we have here so typically, if this loop factor is greater than 1, then this expansion doesn't work, which means the scales, naive scale separation between short scale and large scale. It's not valid. So we usually think that for at least within the linear perturbation theory, large scales are large scale, short scales are short scale. Those are between not possible. So we only know the large scale from, but if we can see, we already see a relatively stable feature in CMB scale, we can say that this never happened. Something like that. So we can indirectly say something about short scale phenomena by considering loop effect for the gravity. And usually the loop effect is very small, as I said, because it's suppressed by this factor, but there could be some motivation to think of enhancement at some scale because we never know what's happening. And also, and actually, the primordial gravitation, primordial black holes are a good motivation to this kind. And also, for the gravitational wave is a very popular topic in cosmology. But people usually only consider this diagram using the equation motion or with a source, because this term is something like fast order times fast order, which is easily accounted in extent. But this term appears because we are doing encode, or we are doing the iterative solution. Right? So many people was not interested in this fraction, but apparently these are two aligned, which are the same. So we have to think. This is what we found in system.
What's the relation between the exciting sparkle and remote black? What was the relation between this excited sparkles and the remote black holes?
Because I don't have it, I didn't specify any model of black holes. For simplicity, I consider some excited scalar. Remote black holes are just motivation. Motivation to think of this.
Oh.
So if you're really interested in this effect, you can choose some model of primary formation and compute. But this is sometimes very difficult. PBH formation models are complicated. So yeah, for the first trial, we consider what happens something at some specific scale.
Do you have any UV divergences?
No, because yes, the UV divergence from the standard ground state. Yes, this is always there. And from this peak, by definition, if you only have some specific range for the contribution, you don't have it. This is a real effect.
Looks like sometimes if you have a left side of the cross would be like the source is emitting some gravitational waves, and then that gravitational waves scattered into the environment.
Yes. Yes.
This happens however soft.
However, what?
However phase.
Yeah, it doesn't much. As far as we have the linear gravitation at that scale.
Is it the usual relation? For example, if we don't consider scale invariant power spectrum in the beginning, say, for example, if NS is equal to 2 at this scale.
Whatever it is, we have the linear gravitation. So the result, this term is E linear times something.
Okay, so it scales together with the 3. I'm wondering an open question. Would you like to give a guess about which characteristic of a model could give a same order or of that to find out?
Same order.
Okay. The second one of the first line, people usually consider the lower diagram.
Mm-hmm.
So just say the lower diagram was missing in real investigation, but it also stated that you expect people should consider the lower diagram. The difference between two diagrams, the contribution, the difference of the contribution of these two diagrams should be model dependent or
Yes.
yeah.
Yes. But apparently the physical processes are different. This is generation of nothing. And this is correction of something. Right? And this scale dependence reflects this difference. So this is nothing from, generation from nothing. So it has to be peaked in scale where something is. And this is a correction for something, so it can scale.
When the higher order also change what the number of counts.
Yes. Yeah, so in principle, this number has to be smaller. Otherwise, the loop expansion. That's up to the expansion, which means the scale separation concept is fake.